this lecture we are going to continue our discussions on central force field motion, and we are going to look at some problems. Overview is that we will recapitulate some of the essential points of motion of a particle in a central force field, and we will look at some problems, application of these relations. Recall that we had studied this differential equation given at the top, which denotes which represents the motion of a particle in central force field with a transformation that u is 1 over r, the radial coordinate, and the solution that we had is c cosine theta plus delta plus gm by h square. Here we set the phase delta as 0 by considering that at theta equal to 0 r is equal to r min. Therefore, we start measuring theta from that radial line where the radial coordinate is minimum, and in that case delta turns out to be 0, and we have discussed these relations. Remember that see here there is a correction, the tangential velocity is v cos phi, and we have h, which is the angular momentum per unit mass, which is h square theta dot is r times v t. So, radius, so this radial coordinate times the tangential velocity is nothing but the angular momentum per unit mass, this angular momentum per unit mass. Okay. Then we looked at the solution of the equation of conic sections, locus of a point which maintains a constant ratio of its distance from a fixed point known as focus and its distance from a fixed line which is called the directrix, and d, as you know, is the perpendicular distance between the focus and the directrix. And by comparing for various values of E, which is the eccentricity, we had discussed about the circular path, and we have also seen how Kepler's third law is recovered from all these expressions. Then we had discussed about elliptic paths. These are the major relations that we had seen in the previous lecture. We have derived all these things. This is for the elliptic path. For the parabolic path, which is for the first time the trajectory becomes unbounded at theta equal to pi, it becomes unbounded. So, this is parabolic path for which eccentricity is 1, then hyperbolic path eccentricity is greater than 1, and it becomes unbounded for values of theta less than pi in the second quadrant, and also in the third quadrant as minus negative. So, something greater than minus pi. Then we had discussed the energetics of motion in a central force field. Everything was discussed in the last lecture, and we had compared the various trajectories and looked at the energy of all these trajectories. For unbounded trajectories, we found that energy is greater than equal to 0. For bounded trajectories, energy is less than 0. It is precisely negative. So, for bounded trajectories, energy, the total mechanical energy must be negative, whereas for unbounded trajectories it is 0 or greater, and we calculated escape velocity, etc. And we also studied the effective potential energy which we have discussed, and we have plotted the effective potential energy and the various levels of energy that we have when r dot. You see, this effective potential energy is the energy, is the total energy when r dot is 0. That means r equal to r min, this effective potential energy is the total energy of the particle, and because that is constant, therefore, it is true for any other value of theta and any other value of r on that trajectory. Therefore, this effective potential energy actually gives us the total mechanical energy of a particle in a certain path. And we have seen how for a circle it is the bottommost point where there is only one solution. So, the radial coordinate will remain constant, and that is marked by R c. When it is an elliptic, and you know the energy, that is the minimum energy of the minimum effective potential energy for a circular path. For the elliptic path, if you now slightly increase the energy, but still energy is negative, then you have two intersections with the potential energy curve, and those two intersections correspond to R min and R max, which is for the elliptic path the perigee is the R min and the apogee is the R max. Or for in the case of a sun, something rotating around the sun, is the perihelion is the closest point of the trajectory from the sun, and aphelion is the farthest. For a parabolic path, the total energy is 0, therefore, it is the R axis in this figure. You can see there is one R min, there is an intersection with the potential energy curve, but there is no intersection on the other side, because the curve is asymptotic to the horizontal axis. It will never reach the horizontal axis, therefore, the solution is unbounded on the other side. There is one R min, but unbounded. Same thing for hyperbola, the hyperbolic trajectory, the energy is positive and it is unbounded. There is one R min, but there is no other bounding. So, these are unbounded trajectories for total mechanical energy greater than or equal to 0, and when it is less than 0, we have elliptic or circular paths. This picture will give you a very good idea of how the energy on various trajectories or orbits or trajectories behave, or under what range, I mean the range of the energy for various trajectories. We start off with this problem, which is taken from the book of Merriam and Craig. A satellite is in a circular earth orbit of radius 2r is shown, where r is the radius of the earth. What is the minimum velocity boost delta v necessary to reach point B? You can see the point B has been marked, which is at a distance of 3r from the center of the earth. At what point in the original circular orbit should the velocity increment be added? The satellite is in a circular orbit, therefore, it has the radius of the orbit is already specified, it is 2r. You can find out the orbital speed. Now, the question arises, what is the minimum, because it is asking the minimum energy boost that is required to reach that point B. When will I have the minimum energy boost? When this satellite will reach B as the farthest point. If it reaches beyond B, any point which is farther than B, greater than 3r, then that will definitely require higher energy. Therefore, B whatever be the trajectory, B should be the farthest point of the trajectory. And because it has started from a circular trajectory which is at 2r, therefore, the nearest point of that trajectory should be 2r from the center of the earth, because center of the earth is the focus, and B should be the farthest point of the trajectory. Therefore, this has to be an elliptic trajectory with r min as 2r and r max as 3r. And now, if this has to be the B has to be the farthest point, then that ellipse must be oriented something like this. So, we draw it in a better way. Maybe this. Okay, so, this will be the roughly the ellipse, with B as the apogee, and therefore, the diametrically opposite point should be the perigee. So, this should be the point from where theta is being measured and theta equal to 0. So, this is R min and the other side is R max. Let us see the solution of this. Here I have drawn that elliptic trajectory roughly. It was initially on a circular path, and you can calculate that V c, the circular path velocity. Radius of the earth is 6400 kilometer. We have to find out delta V min. Now, this V c is the orbital speed on the circular path, V t is the tangential velocity required to reach B as the apogee point. Therefore, V t must be the velocity on an elliptic path at perigee. V t must be the velocity on that elliptic path at the perigee. So, for the circular path, the orbital speed, this we have derived under root g m, the central gravitating mass is earth, therefore, we have to consider capital M as mass of earth. The orbital speed is under root g mass of earth by 2 times r. So, that is the radius of the circular path. So, it was under root g m e by r, radius of the circular path, which in this case is 2 times the radius of the earth. Therefore, V c is this, and if I replace g m e as g e r square, this we have discussed that g m is equals to the acceleration due to gravity on the surface into the radius. In this particular case, it is the earth. Sorry. In this particular case, this is the earth and this is mass of the earth. This relation I have used. So, this is g r square. Okay, so, g times mass of earth is acceleration due to gravity on the surface of the earth times r square, radius of the earth square. Using this relation, I have the velocity on the circular path, the speed on the circular path, which is called the orbital speed, as this, and if you calculate this, it turns out, and when you plug in the values, we know the acceleration due to gravity on the surface of the earth, we know the radius of the earth, and that divided by 2 and under root, that turns out to be 5603 meter per second. This is the orbital speed on the circular path. Now, we know the various parameters of the ellipse. For the elliptic trajectory, we know this solution. This follows from the kinetics, and we have derived from here that 1 by r max plus 1 by r min is 2 g mass of earth by h square, and if you again replace capital G into mass of earth as g e r, radius of the earth square, and h square, which is the angular momentum per unit mass, as 2 r into V t, because why 2 r? Because it is at a distance 2 r, the satellite is at a distance of 2 r here from the center of the earth, from the focus, and on the elliptic path its velocity is going to be V t. Therefore, angular momentum on the elliptic path, angular momentum per unit mass on the elliptic path is equal to 2 r into V t, and that is squared, and this is going to remain constant. Remember, this h is going to remain constant. Now, this simplifies to the acceleration due to gravity on the surface of the earth divided by 2 times the speed on the tangential speed at this point on the elliptic path. From here you can solve for the tangential speed. R min and R max are known. R min is 2 times the radius of the earth and R max is 3 times the radius of the earth. So, one is 2 times R e, the other is 3 times R of the earth, and once you substitute everything, the straightforward algebra will lead you to the tangential velocity at the perigee for the elliptic path, for the particle to traverse on the elliptic path should be 6138 meters per second. On the circular path it was 5603, and on the elliptic path it should be 6138. Therefore, there has to be a boost of 535 meters per second at that perigee point. Once you give that boost in velocity, now it will start moving on the elliptic path. Now, the particle will start moving on the elliptic path and reach B, and that will be the farthest point it will reach, and then again it will come back to the perigee. So, that is the apogee, it will reach the apogee and again follow the rest of the ellipse to again reach back the perigee. So, that is the boost. Okay, the next problem, which is again taken from the book of Merriam and Craig. A satellite is in a circular polar orbit. Polar orbit means it goes over the poles, the north and the south. It is on a circular polar orbit of altitude 300 kilometers. Now, this 300 kilometers is from the surface of the earth, of course. Determine the separation distance d at the equator between the ground tracks, they are shown in dashed lines, dashed curves. We have to find out the separation distance d, it is marked here. This is the separation distance. This distance on the equator, we have to find out this distance between the 2 successive track marks. So, this satellite will go overhead these points. When it comes back again, the earth has rotated, and therefore, the point which is directly underneath the satellite at that point has shifted, a new point has come. We have to find out the distance between these 2 points. So, associated with 2 successive overhead passes of the satellite. Radius of the earth is 6400 kilometer, the height of the satellite from the surface of the earth is 300 kilometer. We have to find out that separation distance of the point of the 2 points on the equator, which will be underneath the satellite when it comes back after one orbit. Now, radius of the circular path in this particular case is the radius of the earth plus the height of the satellite from the surface of the earth. Now, that happens to be 6400 plus 300 kilometers, that is 6700 kilometer from the center of the earth. This distance is now from the center of the earth. The time period can be very easily calculated for a circular orbit. We have done this calculation. You remember that t square is proportional to r cube, and that proportionality constant is nothing but 4 pi square by g times mass of the central gravitating object, which is earth in this case. Therefore, when you take the under root of this time, then so time square, then you get time, which is 2 pi under root the radius of the circular trajectory whole cube by g mass of earth square. Again I have replaced g m e as acceleration due to gravity on the surface of the earth times the radius of the earth square. This is the time period of this circular trajectory. Now, within this time period, how much has the earth rotated? That will give us actually the distance on the surface of the earth. Let us do that. So, first the time period is 90.6 minutes. Omega of the earth, we have calculated this previously also, omega of the earth 2 pi radians, it rotates in 24 hours into 3600. So, that many seconds. So, this is in radian per second. That is the omega of the earth. Now, the distance will be in these many seconds, therefore, how many radians has the earth moved, because the satellite will come back to the same point after 5436 seconds. Therefore, I can calculate what is the angular rotation of the earth in this time, and with that angular rotation I will just multiply the radius of the earth to get the distance on the surface of the earth. Therefore, radius of the earth times this angular displacement of the earth in this one period of the satellite, that turns out to be 2529 kilometer. Therefore, for this satellite when it comes back next at the same point, it will see a point which is separated by 2529 kilometer towards the west. If you notice, the rotation of the earth is like this and the satellite is rotating like this. Therefore, once it comes back to the same point as shown here, the point would have shifted by 2529 kilometer. So, it is now initial point, this point, the new point is 2529 kilometers to the west of the first point. Now, this is a problem of launching some satellite or an object from space or at a certain point in space. It is being launched at with a certain speed in a certain direction from point A, which is in space. Let us look at the problem. A spacecraft in an elliptical orbit has the position and velocity indicated in the figure at a certain instant. Determine the semi-major axis length A of the orbit and find the acute angle alpha between the semi-major axis and the line L. Now, this line L has been shown here. Does the spacecraft eventually strike the earth? This is the question. First thing that is mentioned is this on an elliptic path. Therefore, this satellite was actually moving on an elliptic path. The path has not been shown, maybe something like this, and at this instant, the instant at which it is shown, it has a speed of 7400 meters per second at an angle 2 degree with respect to the vertical. Now, this vertical is with respect, is defined in terms of this line L, and this point A is 1000 kilometers above the surface of the earth. We have to calculate the trajectory of the spacecraft and also check whether it strikes the earth or not. It will strike the earth if the minimum separation from the center of the earth falls below the radius of the earth. That means, the perigee of this ellipse or elliptical path of this satellite, if it is less than the radius of the earth, then it will definitely strike the earth somewhere. First, we calculate the angular momentum per unit mass. We are given this velocity and the speed at this point 7400 meter per second at an angle 2 degree. Therefore, I can calculate the tangential velocity first, v t, which is the tangential velocity can be calculated as this v times cos 2 degree, this projection in this direction, v times cosine of 2 degree is going to be v t. And that is also equal to r into theta dot, that is also equal to r into theta dot. Now, this therefore, we can calculate r into v t. Now, radius is 1000 kilometer plus 6400 kilometer, that is 7400 kilometer, which turns out to be 74 into 10 to the power 5 meter times 7400 times cosine 2 degree, and that turns out to be this value. Now, I can also calculate the radial velocity r dot, which is v sine 2 degree, v sine 2 degree. Now, this here you have to be careful about the sign. Here radius is increasing. If you take v sine 2 degree, it is this velocity, this small velocity vector, which is the projection of the velocity vector in the direction of L, which is the radial line. Therefore, r dot is v sine 2 degree, which turns out to be 258.26 meter per second. Therefore, we have first calculated this constant angular momentum per unit mass h, and we have calculated r dot, and we definitely know v t. We can now substitute in this expression of energy and calculate eccentricity of the path. For example, we find out the energy. Energy is half m velocity square. Now, this velocity square is nothing but this v square, 7400 whole square, half times mass times v square minus g m m by r. This is the net total potential, the total mechanical energy of the system. This is the total mechanical energy of the system, and g m can be replaced as g r square, the acceleration due to gravity on the surface of the earth, times radius of the earth square. So, that is what I have done. And I can calculate the energy in terms of the mass. The mass will later on go away. So, energy happens to be some negative quantity. Mass of the particle is a positive quantity, therefore, energy is a negative quantity. So, this is an ellipse as it is mentioned, and this energy has to be constant over this trajectory. At the perigee and apogee, where r dot is 0, there, because I know h, I know everything, all these things, therefore, I can calculate the energy and substitute, I express the energy. This is essentially the effective potential energy, which we have been discussing. So, the total energy at apogee and perigee is the effective potential energy, and that must be equal to the energy at any point, because energy is a constant of motion. Now, from here I have a quadratic in R. I have a quadratic in R. Here R stands for the radial distance or the radial coordinate of the perigee and the apogee. Why we are getting a quadratic equation? And this should have real solutions because it is an ellipse. Therefore, at perigee and apogee the values of R actually represent the R min and R max. If you solve this quadratic equation and it will have two real solutions, you will get the R min and R max. This is what is expected. So, that is the quadratic equation. If you solve it, you get R min and R max. You see this R min is 7157 kilometer, which is larger than the radius of the earth. Therefore, this is the shortest distance from the center of the earth, smallest distance from the center of the earth. Therefore, this satellite is not going to hit the earth. So, R min is greater than radius of the earth, therefore, satellite is not going to hit the earth, but keep moving on the elliptic trajectory. So, that solves this problem, and you can calculate the eccentricity of the orbit, R max minus R min by R max plus R min, which we have discussed already, and that turns out to be 0.0416. That is the eccentricity lowercase e. Okay. Let us look at this problem now, again from the book of Merriam and Craig. A satellite is placed in a circular polar orbit a distance h above the earth. As the satellite goes over the north pole at A, is shown in the figure, its retro rocket is a rocket which fires in a direction opposite to the direction of motion. Therefore, it actually brakes, it's used to brake the motion of a satellite. So, it applies brakes and reduces velocity. So, its retro rocket is activated to produce a burst of negative thrust, which reduces its velocity to a value which will ensure an equatorial landing. Derive the expression for the required reduction delta V A of velocity at A. Note that A is the apogee of the elliptical path. Of course, it has to be apogee, that is because if this is an elliptical path and if it has to land on earth, then its perigee must be inside the earth, right. It must be less than the radius of the earth. Therefore, A is the apogee. The first step, we write the velocity of the circular trajectory, because we have to find out the delta V, expression of delta V. Therefore, the orbital speed on the circular path, when so at A the orbital speed is same everywhere, I have written it at A. So, this orbital speed is equal to under root g mass of the earth by the distance from the center of the earth, from the focus, which is r plus h, the radius of the earth plus the height of the satellite above the surface of the earth. Now, since the trajectory is elliptic, first we write down the expression of our kinetic solution at theta equal to minus pi by 2. Now, this requires an explanation. This satellite is moving on this path, and this is an elliptic path. This is a hypothetical path, of course, right now. Theta is always measured in the direction of motion from the perigee. Therefore, if this is the perigee line, this point is the perigee, then theta is measured from here. So, that is theta. So, this angle is theta. If it is to land at B, that angle I can say as minus pi by 2, because its angle is being measured from this line and B lies this angle, that the line from the center of the earth to B makes with the line of the perigee is minus 90 degree. Theta is being measured positive in the counterclockwise direction. That is how the satellite is moving. Therefore, at theta equal to minus pi by 2, the radial coordinate of the satellite on this elliptic path, hypothetical elliptic path, which will it will traverse only a part of this elliptical path, of course. Therefore, the radial coordinate at theta equal to minus pi by 2 must be the radius of the earth, and therefore, and that is at theta equal to minus pi by 2, just put theta as minus pi by 2 in the solution, kinetic solution, cos of minus pi by 2 is 0. Therefore, 1 over the radius of the earth must be g m, mass of the earth, by h square. From here I can get the value of h, the angular momentum per unit mass, which is a constant, and from this h value I can equate it to this h value which I have obtained. I can equate it to the small h value calculated from the velocity, the tangential velocity of the satellite on the elliptic path that it should have, times the radial coordinate, which is r plus h. That will give me the angular momentum per unit mass of the satellite at A on the elliptic path. That should be the velocity of the satellite, or the speed of the satellite on the elliptic path at A. So, V A E, and that if I multiply with the radial distance from the focus, that will give me h. So, I have calculated this angular momentum per unit mass from two sides. One is considering that this ellipse must intersect the radius of the earth at theta equal to minus pi by 2, and the other side is from its angular momentum per unit mass at A, and both must be equal because that is a conserved quantity. And from here the velocity on the elliptic path at A should be this quantity, under root g m e r by r plus h. H is the height of the satellite from the surface of the earth, capital H. Therefore, the boost this, in this case it is reduction in speed. The reduction in speed must be the velocity on the elliptic path minus the, or delta v. This is the delta v, is the velocity on the elliptic path at A minus velocity on the circular path at A. Obviously, this is going to be a negative quantity. Delta V A must be a negative quantity because it is a reduction in velocity, and that expression is given here. So, that completes the solution of this problem. Therefore, just to summarize, we have discussed some problems related to the central force field, motion of a particle in a central force field. We have looked at some practical examples from the book of Merriam and Craig, and I have demonstrated how the relations that we have derived for various trajectories are used in solution of these problems. So, with that I will close this lecture.